So let's go with tennis serves by height. Okay, so here is the sum of squares, right, for the tennis serves by height. So sum of squares of the residuals is 497.179, okay? Now, what is the y? The average y is 118. So let's say that I actually add a movable line here. Sorry, hold on. I'm trying to get the right. That's close enough. Apparently it's not. There we go. Okay. So let's actually do my residuals based on that. Okay, so notice the sum of squares based on the average y is 696.547. So, Tyler and everyone else, please notice this. First off, the sum of squares, this should remind us of the standard deviation formula, right? Because when we talk about our standard deviation formula, S of x is equal to the square root of the sum of x minus x bar squared divided by n minus 1. So that's my sum of squares right here. Make sense? And so what an r squared is calculating is a percent reduction of the sum of squares. So this is the maximum sum of squares based on the average of y. And when we do r squared, we're going to do the difference of those two. Divided by the original. And so if the sum of squares for the residuals was 0, I would just be left with this divided by itself, meaning I have perfectly reduced that sum of squares. The r squared would be 1. But what we're finding here by doing that difference is how much were those squares reduced. And so it's a percent reduction in the sum of squares. And so it literally is a measure of spread based on the residuals. It's very heavily tied to the standard deviation. But this is unitless, whereas standard deviation is including the units. Does that make sense? A little. A little. So standard deviation is, let me get rid of this. Let me get rid of that. Okay. So the standard deviation is literally finding the typical amount these residuals, or the typical length of these residuals, how far the data typically deviates from that least squares regression line, okay? And so that is heavily tied to the units, right? And we have a sum of squares based on that. Well, the closer those data points are to a line, the more the lower these sum of squares are. And if we can get that sum of squares really, really, really low, then that means we have reduced this sum of squares to basically nothing. And so it's the percent, and you need to pay attention to this. I'll go ahead and tell you it is on the Demonstrate Your Understanding, and it's regularly on the AP exam, but it's the percent of variation in the y value. So in this case, the speed of a tennis player's first serve and so when we say variation, that's a measure of spread, right? So it's the percent of variation in the speed of a tennis player's first serve that is explained by the linear relationship between height and speed. Right? So there was a lot of variability in that first serve. So what percent of the variation in that speed of the first serve that is explained by this linear relationship? And so because it's about variation, it's a measure of spread. Does that answer that question?
Yes, sir.
Okay. That is also the format that you would want to use when being asked to interpret what R squared is, right? So, yeah, it is the percent of variation in the dependent variable or the response variable that is explained by the linear relationship between your independent and dependent variables.
So when we write it down, it always has to be in percent form. Can it ever be decimal?
Yeah, I would always do a percent form.
Okay.
So like the R squared is, so okay, here's why it's important that it's a decimal. So R squared, I'm just going to make it up here. I don't, actually, do I have it on the previous page?
Where's that at?
Do what? Okay, so R squared is 0.2856.
I can't tell you how to do
And so if I let R squared equal 28.56 and percent, technically it's the same, but if I take the square root of this, it's going to make 28.56 smaller, like 5 point something, right? But when it's this decimal and I take the square root, then that's how we get that R of 0.5344, right? Notice when we take the square root of the decimal, it actually gets bigger. And so that's why it has to be as a decimal here, right? And if I square this, that's how I get to here. But R squared is a percentage. Okay. Is that a what in terms of you have a question?
So what exactly is R squared? Now, like, I know how, like, interpret it.
That is what it is. Like, legitimately, it's the percent of variation in the response variable. So,
Alright, great, that's all I need.
right here. Remember, come on, bring it back. It's not coming back. So, remember how there was all this spread?
Yo,
No, not a regression. Oh, I could. Equals 118. Let's see if that works. And then, so if I show the residuals, oh, it's not going to let me do it for that. Okay.
so what's the difference between, the sum, what is it, sum of squares and R squared?
So R squared, so remember how I took the sum of, this is the sum of squares based on y hat, right? Or not y hat, by the average y. And so when I drew that horizontal line in here, at whatever the average y value is, we got squares from that.
Yeah.
And so that was this sum of squares, okay? This is the sum of squares based on the residuals of my prediction line. So notice how this reduced that sum of squares by about 200. So I'm going to so what we have done with R squared is we have reduced our sum of squares by about 200. So just do 200 divided by 696 for me real quick, just to see what it comes out to be.
Oh, my bad. What is that, 0.2873?
0.2873.
Yeah.
Okay? Look at what R squared is here from the calculator, 0.2856.
Alright, I got you.
So it is the percent of variation in the speed, so in the response variable, that is explained by the linear relationship. So it's how much the sum of squares was reduced by in comparison to the original sum of squares based on the average.
Right, I got you.
Okay? We good with that?
Yep.
Now, questions, comments, concerns? Okay. There's only 2 questions there? Nope, that's not what I wanted. That's what I want. Okay. So agenda. We're going to finish up the set of notes, then demonstrate your understanding, and then AP for your response questions. So not a ton here. I do want to do a quick reminder on this, okay? This is called a mini tab output. Sometimes it comes up. This is also based again on the, we already did this. I don't remember which page it's on. There you go, page 6. So we already did this, but how would I write my least squares regression line from this? Or the equation for my least squares regression line from this?
Y hat
So first off, we need a y hat.
equals 12.05.
What? No.
Yeah, plus 1.4.
Oh, 103
Yeah. X.
times x. And remember your context. So remember, it literally tells us that these numbers are my what? Coefficient. So coefficient of a constant's a little of an odd phrase, but that means it is my what? So the constant, right? The y-intercept. And this is the coefficient for the height, which is my explanatory variable, right? So the predicted height, or the predicted speed, remember I like my context in there, predicted speed is equal to this times height. And so that's all that that's saying. Notice, is it the same r squared as what we just saw on the calculator? Yes. Notice, I think, was it Joseph who was asking about percent? Yes. Yeah, so yes, we report it as a percent. We interpret it as a percent of variation that's been reduced, okay? Notice it gives me my standard deviation, things like that. Thank you. Okay. Questions about that? Okay. The danger here that we wanted to remind ourselves is, what did we learn about the correlation coefficient for all 4 of these graphs? They're all the same. So is it enough to just look at R? No, we also have to look at the graphs, right? Which of these are the only ones that I would really describe as a linear relationship?
The first one.
I would definitely say the first one, and I could make an argument for the third one. It just has that one data point. What do you think we would call this, by the way?
A potential outlier.
A potential outlier. What would we call this one? High leverage, right? Remember, if it's far horizontally, that's a high leverage. If it's far vertically, it's potential outlier. Yes?
Can it be still high leverage if like most of the plots are like in the top right, and then there's like a really low plot, like towards the
So like being low instead of high. So remember, the only way we define that potential high leverage point is if it's far away horizontally. So it doesn't matter which side.
What if it's far vertical and horizontal?
More than likely, one, it'll be an influential observation as well. And so based on that, it actually would end up probably being neither, because it's actually going to be, well, let me think on that one before I state for sure. Good question. Okay. I will say this, they're not going to do that to you, but that is a fantastic question that I want to do research on. So, we already talked about it. High leverage, what does that mean? Far, so this is on page 7, far horizontally from the rest of the data set. Outlier, far vertically from the rest of the data set. And are we ever going to call points high leverage or outliers?
No.
Potential high leverage points, potential outliers. And then what is an influential point?
That's just the category that both of those belong to.
They can both belong to, but I will say not all high leverage points, not all outliers are super influential. So that's what I would say. If you have one that's far away horizontally and far away vertically at the same time, but it's in line with the rest of the points, it's definitely not going to be an influential point. Because what does an influential point do? It can change the slope significantly, the y-intercept, the correlation coefficient, so the standard deviation. So if it affects one of those values significantly, then it's influential, right? So if we have this set of data points, and then I have one way out here, is that going to change the line or the slope or the correlation coefficient very much? So that's far away horizontally and vertically. I would not call that an influential observation. Does that make sense? Okay. So, to help us with this, right? Well, here's a scatter plot of forest area in millions of acres and numbers of tree in billions for each state, excluding Alaska and Hawaii. Describe the effect the point representing Maine, 17.6, 23.6, has on the equation of the least squares regression line, S and R squared. I will point this out. You're not going to have to explain or tell exactly what the numerical values are. It is more going to be about just explaining, does it increase, decrease, stuff like that. Okay, so I want you to talk about that with your small groups for a little bit. So Haley, if you want to join one of the other groups so you can talk. Just a couple of minutes, come up with your answers. We're going to come back together and discuss A. So,
It's not really changing the line, it's not.
Yeah, that's why I moved.
Yeah, so it definitely would change the slope of the line.
Oops, sorry, I hit you.
Change the slope of the line.
Definitely closing anything.
so it's going to change the sum of squares. What is that going to change based on
The sum of squares would be big.
So that changes the
And
standard
then R
deviation.
squared.
And so be careful, when we say sum of squares, we don't know about the sum of squares of the residuals, right? Not the sum of
Like,
squares of like
the variation
average
is-
y or anything like that. but the sum of squares of residuals. So that would change S. Is there anything else that would change?
Is there a way for us to see? Like,
That rate
the line is
Maybe. Does it look like that? So like if I got rid of this, does it look like that line
There,
would
maybe
change?
come back to
No,
down.
so does it look like it's gonna change anything about the regression line?
Slope line.
No.
Oh, so.
What about R and R squared? So it is causing those to decrease?
I'm going like
Higher
Let me ask you this, is it introducing more variability or is it helping reduce variability?
Why is that really far out?
Okay.
that should be bigger, so
So potential.
because it's sum squares.
I know that we probably don't have it all written down, but it looks like we've had good discussion about it. So let's talk about a couple of things. One thing I should have mentioned, and this is going to help with explaining if it's going to change the equation or if it's going to be a high leverage, nope, not high leverage, influential observation is, ask yourself this. If I take that point away, would it heavily change the equation?
Yes. Maybe. Possibly.
So maybe.
Potentially.
Think about it. If I take away this point right here, do you think it's going to change that line very much?
Nah.
I guess not.
I mean, doesn't that line look like it would go about the same space?
Yeah.
So, is it going to affect the least squares regression line?
Not much.
Not really, right? So, not much of an effect on the equation. What about S and R squared?
R squared, if it went away, would be stronger. It'd be higher.
Be careful. So, what measures strength? R. What does R squared measure?
R squared, but if R is
The
bigger,
percent of variation.
then R squared would be bigger.
I know, you're not wrong. I'm not saying that it wouldn't be stronger, but we need to be careful of what we're saying. Because if you had made the argument that R, the correlation is stronger, you're dead on, right? But if you say R squared, you're talking about the coefficient of determination, you're talking about the percent of variation that is explained by the linear relationship. They are very heavily connected, but you have to be careful of that language, right? So the correlation, 100%, if I got rid of this, that correlation would be what? Stronger. The percent of variation in the tree, number of trees that is explained by this linear relationship would definitely, that percent of variation would increase, right?
Yeah, that's what
So do you
And
want a
understand
higher or lower R squared?
What do you think?
Obviously higher.
Lower.
So, and so I know this sounds backwards, but think about it this way. if the sum of squares for the residual, if it's a perfect line, what is the sum of squares for the residual? 0, right? So the sum of squares for the residual would be 0. So then, in an example like that, I'd be left with 696 minus, or I'm just going to do 696, minus 0 divided by 696.
That'd be 1.
And that would be 1. So if it's a perfect line, what is r squared? 1. The sum of squares, the residual sum of squares is 0. But what is the r squared? 1. Which makes sense because if I take the square root of 1,
Higher
right? So if I take the square root of r squared,
than
r is equal to 1. And so if it's a perfect line, what's the correlation coefficient? 1. Now I do have to point out, if r squared is 1, is r 1?
It could be negative.
We got to remember it could be a positive or it could be a negative. Whether the line is increasing or whether the line is decreasing. Right, so if the slope is positive or negative. So don't forget, just because r squared is 1 does not mean r is 1. It could be a positive or a negative.
So r squared is increased by the point and r is decreased.
By this point,
Yeah.
if we remove that point, r squared increases, right? But that point right now is decreasing. So currently, it decreases r squared, meaning less variation is explained. So currently decreasing r squared, and what's it doing to s?
Increase.
I thought,
And, go ahead.
I thought it would decrease r.
It would decrease r. But if r goes down, r squared also goes down. Think about it this way.
Oh yeah, I was thinking about it wrong.
Yeah.
Yeah. I
So if r is 0.8, r squared is 0.64. If r is 0.5, r squared is 0.25.
Yeah, I was thinking about it the other way around.
Yeah. So it's going to decrease r squared, and it's going to increase s, the standard deviations, right? And don't forget, if it decreases r squared, it also decreases r, correlation coefficient. You good? But what's it going to do to the equation? Or what's it doing to the equation?
Not changing
Not much.
very much.
So equation doesn't change much. All right. So B, keeping this in mind and thinking through these things as well, describe the effect the point representing Texas, 41.0, comma 19 has on the equation of the least squares regression line. So at this point right here.
Very little.
So it's doing very little for it.
Yeah.
So if I remove this point,
Yeah, you'd probably be fine. Because it still
So-
fits the rest of the point.
Austin's not as convinced. Austin, come up here real quick for me. Alright? And if I remove this data point, where do you think the least squares regression line might be?
Honestly, more like. Okay, wait, I think that's like.
Wow.
Maybe like. Right here.
Okay? What do y'all think for that least squares regression line?
It can't be, because Texas is already below it, so there can't be, line be lower when you remove the lower point.
Okay? There's another thing I would think about.
Like it would be going more towards Maine, I guess.
Maybe. Remember also, in general, what does the least squares regression line need to do to all your points? It needs to split them in half. Haley, why don't you come up and...
Yeah, I kind of didn't do a good one.
You're good. No, I mean, it's a good learning opportunity. Haley, come tell us or draw what you think the least squares regression line might be without that data point. You can erase that if you want.
You can erase my line. You bet.
Okay. So would that split it more in half?
Yeah.
Yeah. It doesn't change it too much in that case, does it?
Not really.
I will say this, I think if I were to draw the least squares regression line, it might look something more like this.
That makes sense.
You can start it on the x-axis.
Well, so remember this data is gonna, yeah, I mean, it's not really starting on the x-axis. The line just needs to minimize the sum of squares. The line will intersect the y-axis down here, right? So I can see why you were thinking of that idea of like it has to intersect the y-axis before the x, but it does not.
Oh.
So what would you say, like minimal effect on the RL?
I don't know. If I look at the original versus what my red is, what do you think?
Big effect.
Like the last one?
I mean, that slope changed pretty significantly, didn't
How
it?
it affects that.
So it's an influential point.
It would be an influential point. You're asking how would it affect it that much?
Yeah.
It's really far.
So because this is horizontally far away, it's gonna pull that line towards it. Most high leverage points are going to pull the least squares regression line towards it.
I got you.
So because it's a high leverage point, it's horizontally far away, it's gonna pull that least squares regression line to it. Here, right, if I remove that point though and only focus on the others, which I might have even overdone it a little bit, I might do something like this. Here. Right, notice it's very close to all these data points, it's pulled up towards that outlier a little bit now because that one point is gone. Now, you're not gonna have to do this perfectly, but we do wanna recognize this idea that that high leverage point affected the least squares regression, or it affected which part of this the most?
The line.
The line.
It affected the line, right? So, the slope would probably, or we'll just say it heavily affects the line, the heavily affects the least squares regression line. But what about r squared and s? Do you think that point increased or decreased?
It'd be roughly the same because it's pretty close to the line.
It is pretty close to the line, so like if I lose that data point that's pretty close to the line,
You're not losing any points.
well, maybe not, but notice like by this pulling it down, it kept us close to these points as well, didn't it?
Yeah.
Now these residuals have become significantly
Large.
larger.
But the other ones got smaller.
Some of the other ones did get smaller. Typically, though, and I will say this, typically, a good rule of thumb is a high leverage point reduces the variation, reduces r squared. So if I get rid of that data point, what's going to happen to r squared? It's going to, no, decrease, right? Yeah, sorry, so that point reduced the variation, so if we get rid of it, the spread is going to increase. So that point reduced r squared and s, so both increase if the point is gone. Now, I'll go ahead and tell you, it's not a hard and fast rule. Don't sweat it a ton, but it's a general rule of thumb. And the bigger thing is going to be just identifying potential ones. I'm going to do some studying to see how much they actually ask you to explain how removing it would affect the line, but I don't think it does a ton. So an important question here is, does the forest area appear to cause an increase in the number of trees for each state?
Yeah.
So listen to my question again.
Or no.
Does so we have a positive slope. So if the area of forest increases in a state, does that appear to cause an increase in the number of trees?
There's an association, but
You can't cause this.
Yeah.
you can't prove causation with this.
And that's what we need to recognize. Is there a high correlation?
Yeah.
Yes, but it does not cause it, right? That's why Texas is a little bit different. How many trees are there in Texas?
None.
Not none, but it's definitely not as many as we would see in other states, right? So, let me run like a wind bullseye. So again, does association imply causation?
No.
No, right? An association does not imply causation. What do you need for cause and effect? An experiment. And remember, the whole point of all the elements of an experiment is to reduce what?
Confounding.
Confounding. Right, Bryson?
Yes, sir.
What did we say?
I said, oh, we call it cactus, it's trees. And then Logan said, no, it's not trees, it's a type of plant, and I was like, are we sure?
So the question is though, what does an experiment do that allows us to establish cause and effect?
It only,
It reduces something. There we go, right? We got to immediately think of that, right? As a quick recap, as a small thing, Haley, give me one thing we can do in an experiment to reduce confounding.
Blocking.
Blocking, okay? And what do we need to do within those blocks? We need to,
Have similar data or similar people.
they need to be similar in some way, but there's something else we need to do within them, Lexi.
Do you randomly assign?
So remember, we randomly assign the treatments within the block, right? So that we reduce that variability. What else can we do? Josh, give me one more thing.
Blinding.
So we can do blinding, right? So blinding the experimenter, blinding the subject can reduce confounding. Joseph, you remember any others?
Just random assignment in general.
Just random assignment in general, right? So a completely randomized design versus a blocked design.
Direct,
Say again. We want control groups. What are you saying?
direct manipulation.
Direct, not direct manipulation, direct control, right? So a control is when, or a control group is when there's no treatment, right? Direct control is when we make sure that one variable stays the same. Remember how all of y'all were like, man, that Stanley Milgram experiment, they should have used men and women, right? Equality, but what did they do?
they only use.
They only used men. Why?
To reduce.
Blocking.
To reduce confounding. That was an element of direct control. Now, could they have used men and women and done blocking? 100%, right? But they used only men, one, because only men were officers in the Nazi military. But two, they only used men because it reduced confounding. Direct control of that potentially confounding variable. Y'all are missing one of the big ones though. Huh? Replication, thank you. Can you do it just one time? No, you gotta show that it's repeatable. Replicable? That's the word, not repeatable. Don't. Replicable? Alright, now, I need us to get, this is literally the last thing, and it's not going to be a ton, but this is important. Is all data linear? No. So what can we do if the data is not linear?
Nothing.
That's not true. Huh?
Do something different.
So there's two things we can do.
Call Mr. Matt.
We could add a negative part of it.
Okay, maybe. Alright, so do this for me. Turn on those calculators. I need you to add either a list and spreadsheets page or a data and statistics page.
Here it is, this page.
Yeah. I'm loving the terrible dad jokes. I'm ready for it. Alright, looking at it here. So hit menu no matter where you are and go to statistics. And where do you think I'm going to tell you to go from here?
Stat calculation.
Stat calculations.
Are we still listening this data?
It doesn't matter. It actually does not matter whatsoever. I just want you to see options. Are linear regressions the only options?
No.
Oh,
So what are we going to do?
The other one.
whatever matches.
We could do quadratics, we could do cubics, we could do power, we could do exponential. Essentially, we can fit a curve to the data instead of a line. That's option one. We can fit a curve to data instead of a line. Now, in AP Stats, we don't do that, so don't sweat it. But that is option one. I just want you to be aware of that, okay? So make a note, because it literally says, you know, what are the two approaches. So, one, fit a curve to the data. Okay? Two, and this is what we actually do most of the time. This is actually where most of the regression comes from. Anybody know what type of curve this might be here? It looks pretty darn exponential to me, right? Okay, so watch this. So I'm going to make a graph page, and here is e raised to the x. No, that's not what I wanted. I wanted the number
I hate
e.
you.
I'm sorry you feel this way. E to the x. Now, does anyone remember what the inverse of e to the x is?
Natural law.
The natural log of x. So what happens if I do the natural log of e to the x? What do I get?
Straight line.
I get a straight line, I just get y equals x. So you are not going to have to do this, but this is what I want you to hear. What you can do is you can make the data linear
Find the area.
by taking the inverse of whatever shape it is, right? And so if I had data that looks, so notice like this has flat and then it increases. But what if I had data that looks like this, just kind of straight up? What do you think I would do to that set of data?
Take the square root.
That looks like half of a parabola, doesn't it? So I'm going to take the square root. And so the whole idea is, option 2 is linearize that data. I had a red marker somewhere, and then someone stole it. Why else? There it is, found it. Okay. Okay, so to linearize the data.
Is that a real word?
No.
How do you linearize the data?
It is by using the inverse operation of the shape. So, once we get to review, I'll show it to you. I just want to focus, but, well, I'm going to show it to you here. So you see right here how this is exponential in shape? So what we're really saying is that the y is exponential in shape.
Yeah.
So for every y value, so I would leave my x's the same.
The lid was not on.
So I would have my data values x and y, and then I would just literally take the natural log of y. And so I would graph x and natural log of y for my scatter plot.
Why are we doing that?
Well, because this is exponential. You can do a common log as well, but
I forgot we have to do logs for stuff.
so then I would just do 3 and natural log 4. Say again. Yes, make it the restaurant. But again, hey, listen. We're not going to ask you to do it. You just have to understand the concept. And there's an important part to understand. Yes.
I think that was natural log and not just some random log based.
Hey, guess what? It don't matter. We're in a mathematical science. We're not doing math. Okay. So listen.
Hate that.
By the way, oh dang it, she left. Yes, linearize is a word. Okay, so showing the length and weight of Atlantic Ocean rockfish, would a linear model be appropriate here?
Probably not.
Heck no. Does that look like a line?
No.
No. Notice if I were to create a least squares regression line, maybe something like this. Do you know what I would see if I created the residual plot?
You would have
A lot
parabola.
of boxes.
I would have a very clear curve. Do we want a curve in my
No, you
residual plot?
No.
No, I want that residual plot to be scattered, no pattern whatsoever. Okay, so there are several ways we can attempt to linearize a curved association. We can use powers, we can use roots, and we can use logarithms. So does it have to be natural log? No, a lot of times we use common log as well.
What is common law?
Log based 10. Again, you're not going to have to do it. We just have to understand how it works. So here is actually what they did for this one. They actually cubed each of the x values. That's one option. Did it linearize the data pretty well?
Yeah.
So they kept every y exactly the same,
Why would you cube?
and they cubed the x values. Oh yeah, fun fact, and this is why we don't have to do it on the AP exam, because sometimes you just have to play around with it, and you go, hey, I think it's going to be a natural log, and then it doesn't work out well, so then you try doing a cube root of the y values, or cubing the x values, so you can do it to either the explanatory or the response. The priority, hear me again on this clearly, the priority is making sure the data is linearized. So they just have to play around with it until they find something that works. Now, let's look at this. So you should have the Minitab output at the bottom of that scatter plot there, right? So what would be my least squares regression line for this problem? 0.066,
Wait, why do you use that?
And then,
because that's what?
Oh, wait, yeah.
Wouldn't it be y equals?
Plus.
Okay, so we need to back up and say y equals, is that right so far?
Y
hat
Y hat equals, okay,
And then plus 0.014x.
plus 0.014
Would it not be the
Uh,
cube root of that?
x, say again?
Would it not be the cube root of that?
Close, look again at what they did to x.
Oh,
They cubed it, right?
Yes.
And so we would actually need to do x cubed here. So we linearize the data by cubing the x values, so it'd actually be x cubed. But this again, where I would probably put a length
Oh, so they already cubed it.
cubed. Right, they already cubed. So to get this linearized set of data, they cubed those x values.
Wait, should we cube it or cube root it?
Cube it.
So was they already
reverse
cubed?
it this time? So you keep it, you
Why am I cubing it again? Now I'm like,
Or you cube that.
Oh, we're cubing it. I hate that.
So remember this linearized set of data, I was trying to make sure I'm right on this. So look at it this way, right here, Deacon. You see how all of these numbers are the cubes,
Yo,
x being cubed? So my explanatory is literally the x cubed. So like to get this prediction line, these are the lengths cubed. So whatever the actual length is, I need to cube it for this line to work.
Right.
Okay? And so the predicted weight would just equal this. So how would I find the predicted weight here?
You would plug it in for the
Plug in your x value.
Yeah, you just substitute the 36 centimeters in for length. It has not changed, so find out my predicted weight real quick. So the predicted weight is, you said 600
Yes, sir.
and 50,
657.25.
okay? Missing something with that. Any guesses? Units, which would be, I think, does it say grams there?
Wait, what'd y'all get?
657.25 grams,
Yeah,
right? And so,
I did not.
you did not?
Oh, I forgot.
Nothing close?
Ish.
Huh, it is a little bit different.
I didn't use the entire decimal, but I don't think I do that.
That might have been it though.
I'm gonna do.
So you rounded it up, right? 0.0147, when it should probably less. And so it just depends on where you round the decimal. So I want to go back and I want you to look real quick. What was the length of the fish that we were just looking at? 36 centimeters? So 36 would be somewhere around here. And if I go up, I'm a little off actually. Here. The 657 grams makes sense.
Yeah.
Pretty
close.
It does, doesn't it? Right? And so,
That's 609
yeah. So it'd be about 657 grams. So that's how we use that model to find the predicted weight. So we linearize the data first. And that model works pretty darn well. Okay. Notice, what did they do this time? So this is the very next part. Next,
They did the cube root of the weight.
they did the cube root of the weight. Did that linearize the data pretty well?
Yeah.
So is there more than one option?
Yeah.
Yes. So, oh yeah, you good?
Yeah.
Okay,
Fair.
Okay.
Spacing out.
gotcha.
Sorry.
So,
Advantage in.
here's what we need to recognize. How would I write this least squares regression line?
Y hat equals.
Y hat equals, so what is my y again? That is the weight?
Wait.
You sure that's right?
Wouldn't it be the cubic root of weight?
Yeah, that's the cube root of the predicted weight is equal to,
The 4.066.
Nope. We have a different equation now.
Negative .022.
Yep.
plus 0.2466 times length. Notice in this case, Haley, because you were a little freaked out that it hit the x-axis first, or that it can hit the x-axis. If it hits the x-axis first, it just means we have a negative y-intercept. Is it okay to have a negative y-intercept?
Yeah.
Yes.
So do you usually keep your x in the equation?
Say again.
So what are we doing?
What do you mean?
Why are we using those numbers?
Well, there's the coefficient of the constant, so there's my constant. There's the coefficient for the length.
they are.
And then we took the cube root of the weight. That's why it's the cube root of the predicted weight.
Is this gonna be
So
a
it's-
review today?
Not this. There's one thing that will, but it's super easy.
But nothing about logs and,
Not about writing the equation like this. At least when there's a transformation. But you should be able to do y hat equals the constant plus that times the variable.
it's just a,
It's just the transformation, and that won't be there. Yes. Okay, so don't stress that. Okay. All right. So, last couple details. Right here. Notice, if you look at the very next one, after that, after where it says progress check B, what did they do in the model for progress check B?
It's very strong.
No. What did they do? They took the log of both variables. Did that linearize the data?
Yeah.
So is there just one set transformation that works?
No.
No, right? And so they took the log of both sets of data. So we would just literally write this as the log of the predicted weight equals negative 1.899 plus 3.049 times the log of the length. They took the log of both variables. Okay, and then we can use that. And if you use that, you're going to get this roughly the same predicted weight every time. So after we linearize, and this is the important question, after we do a transformation to try to linearize, what do we not want to see? Any guesses?
Not a curve.
Yeah, we don't want to see a curve. We don't, after we do a transformation, if it's not a line, we messed up. And we just try it again. So if you look at the next two, the last two here, the transformation that they did, what does it say? I can't read it on the slide, sorry. Okay, so we have this again that kind of looks exponential, right? And so they took the natural log here. Does that really look like a straight line? No. If I do a residual plot, so I do a least squares regression line, and I do a residual plot, am I going to see a curve around that line?
yeah.
That's all I really need you to understand, is after a transformation, what do I not want to see? A curve. I don't want to see a pattern in the residual plot. And so, to answer your question, is it in here? To answer your question, Haley, and so I am jumping a little bit. Actually, let's do this quick. Do you need to be able to create a model using transformations from raw data?
No.
No, right? What you will have to do is you'll have to identify, or you may be asked to identify which one is the best. Okay? So, how would we know when we have the best transformation?
There's no curve.
So, what do we look at to determine if there's really a curve? So, does R tell us if there's a curve?
R squared.
Look right here.
The graph,
What is this that they have graphed?
the residual plot.
The residual plots. Which of these residual plots tell me that I have the best linearized set of data?
The third one.
Model two.
Probably, I mean, that's got the most scatter without a pattern, right?
Yeah.
Does this one somewhat work?
Yeah.
Yeah, but it's not perfect. We definitely don't want this one.
Yeah.
That's what we would need to recognize, and that's the big thing that shows up on the AP exam. So, as a part of the American Presidency Project, the annual State of the Union address has been analyzed going back to the first president. Turns out the president's use of the word America has increased in relative frequency over the years. Here's a linear regression output for 3 different models. Notice this is the percent of time that the word America has been used versus the president number, where the president number predicts how many times they've said America. Is just that traditional linear regression a good fit?
No.
No. So what did they do in model 2?
The log of both.
They took the log of both. Is that great? No. Here, they took the log of the percent of America. Does that have a good linear fit?
Yeah.
That's what I need us to recognize. If you look at r squared, this r squared is actually higher than this one,
What?
right?
Yeah.
But this r squared is the highest. This has the lowest standard deviation, but this one has a pretty decent one. Okay? So, after we linearize our data, what do we want to see? And this kind of goes back to that previous question. After we linearize our data, what do we want to see? One,
No pattern.
so no pattern in the
Residual plot.
residual plot. So we want to see lots of, so need scatter in that residual plot. What else do we want to see? We want to high something.
R squared.
We want a high r squared, and as a consequence,
Lower S.
r, well that too, r needs to be close to what? You sure?
Close to,
L1.
Sure?
Oh, wait. 4 negative 1?
Thank you, there we go. Right? It matters whether it's positive or negative, okay? So high r squared, r needs to be close to 1 or negative 1, and low standard deviation. That's what we want to see. And ladies and gentlemen, well, we still have one thing, but it's not, I'm not going to test you on it. That is AP Stats.
Alright,
Minus chi-squared.
I will not be sure.
We will be reviewing next week. We will still cover chi-squared next week. We will be presenting projects next week and taking the final
I will not
test.
be
Yes,
there.
Billy.
Field trip, right?
Yes. So we will still cover it.
field trip.
Yeah, we have a
I couldn't. I talked to Dr. Johnson and he wasn't able to make it happen. Yeah, they're doing renovations at
We can
UWA.
We could just go somewhere.
we have a field trip to
We could go to UA's math
We have a
campus.
field trip.
Where's
They have a
Okay.
math quad.
So,
True,
listen, to end today, we're going to do a demonstrate your understanding. Tomorrow, we're going to do some AP free response. I'm going to introduce you to chi-squared, and then Monday we take our test and end, and then we will just do review for the rest of this course.
We pull our grades up.
I don't need a review. I don't need a review.
Huh?
We pull our grades up.
Well, I'll have to figure out how I'll do that, but after the AP exam is over, my design is to help you pull your grade up.
But you could make this a little harder.
We'll have one project.
We haven't taken the class test yet.
Okay. You can have your formula sheet out. I don't think you'll need it very much.
I'm gonna get into the
Oh, I knew one of them.
keys.
Let's see if I got it.